In this lecture, we'll be solving linear inequalities. When solving a linear inequality, you use the same technique as solving a linear equation with one difference. If you multiply or divide by a negative number, you must flip the inequality symbol. Let's solve each linear inequality, graph and write its solution set in interval and set builder notations. We'll follow the same technique as we do with linear equations. We don't have any parentheses or fractions to eliminate. We don't have like terms on either side to combine. All of our variable terms are collected on the left side, which means that we got to move all of our constant terms to the right. We're going to add 6 to both sides. This gives me x is greater than or equal to -5. This is the solve part. Now we want to graph it on the number line. I start by finding -5 on the number line. We want x to be greater than -5. Greater numbers are to the right, so we shade to the right. We make sure to put an arrow at the end to indicate that our shading continues on forever. We need to determine whether we're going to use a parenthesis or a bracket at -5. We refer to our inequality symbol to make that decision. Since it's or equal to, we want to use a square bracket. There's our solve. Next, we need to write our interval and set builder notations. I always feel like if I have a graph that the interval notation is staring me right in the face. With our interval notation, we want the very smallest number represented by our shading. So looking at the red, the number farthest to the left is -5. And we want to use a square bracket and -5 to indicate that we are including that number in our solution set. And then our very largest number, looking to the right, I have an arrow. Forever to the right takes us to positive infinity, and infinity always gets a parenthesis. Our set builder notation always starts the same. It's a set of all x such that some condition. The x's that we want this time are the x's that are greater than or equal to -5. So that's what gets put into our our set builder notation. X is greater than or equal to -5. Our next inequality to solve is -3a is greater than or equal to 12. We have no parentheses or fractions to eliminate, no like terms. Our variable terms are on the left. Our constant terms are already on the right. The only thing we need to do to solve here is to divide by -3. But since we are dividing by a negative number, we got to make sure that we flip our inequality symbol. And what I mean by flip is change it from greater than to less than. We get a to be less than or equal to -4. Again, please notice the change. Now that we've solved our inequality, we want to graph it. I'm going to start by finding -4 on the number line. A is less than or equal to -4. The smaller values are to the left on the number line. So we're shading to the left and making sure to put an arrow at the end. Our inequality is or equal to, indicating that we are including -4. Therefore, our graph is going to need a square bracket. Next up are our interval and set builder notations. We want to start with the very smallest x value, which is farthest to the left. I see an arrow, which means I'm going all the way to -infinity. And infinity always gets a parenthesis. The very largest value we have in our shading, the one farthest to the right, is -4. And our graph tells us we want to use a square bracket. We are including -4. Last up is the set builder notation. It's going to start the same. It's the set of all A this time, since our variable was A. And the A's that we're interested in this time are A's that are less than or equal to -4. Our next example requires more than one step for solving the inequality. I don't have parentheses or fractions to eliminate. I don't have any like terms to combine. I do, however, have variable terms and constant terms on both sides, which means that I can choose which side to move my variable terms to. I'm going to move the term with the smaller coefficient, which is -4. I'm going to add 4y to both sides. Gives me 9y plus 3 is strictly greater than 6. Now that all of my y's are collected on the left, that means that my constant terms have to move to the right. I'm going to subtract 3 from both sides. So 9y is strictly greater than +3. The last thing I need to do is divide by my coefficient. Nine does not go into 3, so I know that my answer is going to be a fraction. I need to simplify my fraction. 3 over 9 simplifies to be 1/3. There's my solve. I'm going to find 1/3 on my number line. Y is strictly greater than 1/3. Greater numbers are to the right. It's a strict inequality, which means that I don't want to include 1/3. To indicate that in my graph, I'm going to use a parenthesis. Now we're ready for our notations. Interval notation, this very smallest number represented by our graph here. We're going to be just shy of 1/3. So to indicate that, we're going to put 1/3 with a parenthesis. That parenthesis tells us we're not including 1/3. The very largest value, we look to the right, we have an arrow, which means forever to the right, all the way to positive infinity, and infinity always gets a parenthesis. Our set builder notation always starts the same, the set of all y this time, such that some condition. The y that we want this time are y's that are strictly greater than 1/3. In our next example, we see that we have parentheses. So I need to start by distributing. 1/4 times x, 1/4 x. 1/4 times 4 is a +1, strictly less than. 1/5 times 2x, 2/5 x. And 1/5 times a +3 is +3/5. I have an inequality full of fractions. I would like to get rid of those fractions. We can do so by multiplying each one of our terms by the LCD. The LCD between 4, 1, 5, and 5 is 20. So I'm going to multiply each one of these terms by 20. So we're going to have 20 over 1 times 1/4 x plus 20 over 1 times 1 over 1. 20 over 1 times 2/5 x plus 20 over 1 times 3/5. The whole point of doing this is to eliminate our fraction, so we want to cancel those denominators out by simplifying. 4 goes into 20 5 times, 4 goes into 4 1 time. When I multiply straight across, I get 5x. In our next pair, our denominators are already 1. Nothing cancels. This becomes plus 20. Our first pair on the right side, 5 goes into 24 times, 5 goes into 5 1 time, multiplying straight across, I get 8x. And our last pair, 20 and 5 are both divisible by 5. 5 goes in there 4 times, 5 goes in there once, multiplying straight across, I get 12. Now we have an inequality with no fractions in it. I want to get all of my variable terms on one side, all my constant terms on the opposite side. Typically, when I'm solving an equation, I always move the variable term with the smaller coefficient. When I'm working with inequalities, I always put the variable on the left side no matter what. So I'm going to do that instead. I'm actually going to subtract 8x this time from both sides. Gives me negative 3x plus 20 is strictly less than 12. I always put the variable on the left side because if I have the variable on the right side, most of the time I end up shading the wrong side of the number on the number line. So to be proactive against that mistake that I know that I typically make as an individual, I just always put the variable on the left. Now that our variable terms are on the left, we got to move that constant to the right. I'll subtract 20. Negative 3x is strictly less than negative 8. Last thing we need to do is divide by our coefficient. Notice that we're dividing by a negative number. So since we're dividing by a negative, we got to make sure to flip that inequality symbol. So this is going to be x is strictly greater than, we have a negative divided by a negative, which is going to be positive 8/3. There's the solve. Now we want to graph it and write our notations. For the graph, I'm going to start by finding 8/3. We want x to be greater than 8/3. Greater is to the right. So we're going to shade to the right. Use an arrow. It was a strict inequality, so we're going to use a parenthesis at 8/3 to indicate that we're not including that in our solution set. Next up are our notations. Interval notation. Our very smallest number is 8/3, not included. And then our very largest number, with that arrow pointing to the right, is going to be positive infinity. And infinity always gets a parenthesis. Set builder notation always starts the same. The set of all x such that. Our condition this time is that x is strictly greater than 8/3. Lastly, in this lecture, I want to do an application problem. A couple will spend at most $3,000 for a catered party. If the catering company charges a one-time fee of $200 plus $32 per person, find the greatest number of people that can attend the party. This at most $3,000 tells us that what we're spending has to be less than or equal to 3,000. The catering company charges a one-time fee of $200 plus $32 per person. The number of people is our unknown, and that's going to be less than or equal to 3,000. Now we want to solve our equation. All of our variable terms are collected on the left, therefore our constants move to the right. $32x is equal to 2,800. Dividing by our coefficient, we end up with x is less than or equal to 87.5. Going back to our question, rereading to make sure we've actually answered the question. We're asked to find the greatest number of people that can attend. Half a person cannot attend. Therefore, the maximum number of people that can attend, 87 people.